Who knows? Okay. All right. So today, all right, let me put out a couple things. So today we're going to talk about potential temperature. So we've talked about fresh water and we've talked about salt as budgets. Potential temperature is a thermodynamic quantity. It's a lot like temperature, but it's not the same as temperature. So we're going to talk about what that is, but we're also going to talk about the global energy budget, and in particular how we get that for the ocean, and so where the warm water is, where the cold water is. We'll start to think about that some. The Colling book, the Ocean Circulation book, has a really nice discussion in chapter 6 of the basic stratification profiles in different parts of the world. So even if you, I hope you've all been plugging away in Wunsch and are still like staring at those equations in chapter 3, which is, we're going to continue talking about that for a while, but this is a nice thing to look at. You might also look at chapter 1 in Colling, which is just kind of a big picture of like what's going on in the oceans, and that has a little bit to do with what we're talking about today. That book is free. If you go through the link on the syllabus when you're on the on-campus website or on VPN, click through a couple of links and then you'll get to a page where you can download PDFs. So go ahead and do it if you would like to look at that. And it is a very good book for figures. It has really beautiful schematics. It doesn't have a lot of words, so the figures are really nice, and I'll be using a lot of them as we go in to talk about the dynamical concepts. But it's a nice book to go check out. Okay. Boop. All right. So, all right. Before we get onto the energy budget, which we started at, we're going to get back into that in a little more detail than we got to last time. And we're just going to start talking about thermodynamics at the end. Or this will be most of the class. This will be quick. I wanted to give you a couple of, since we're about a week out from when the first paper is supposed to be due, I wanted to give you some info about that and have the opportunity to questions. So if you want, you do not have to use LaTeX. If you do want to use LaTeX, this is a good opportunity to learn how to use it in this class. LaTeX is like Microsoft Word or Google Docs, but it is like way better for science because it allows you to do equations in a really compact way, and they look really pretty when they're done that way. And it allows you to resize figures and stuff, which at first it's extremely hard to learn, but once you're using it, it is way faster. So it's, and the other great thing about LaTeX is that I've been using LaTeX for 30 years, and it has not changed. It will be the same 30 years from now. It's like Unix. It's written once and for all to be the way that it is. So new features get added, but the same, my PhD thesis still compiles in LaTeX just fine and looks the same as it used to. So unlike Word and other things that are always changing and getting complicated and adding new pieces, you only have to learn it once. Anyway, the cool thing for this class is you can actually open the template for the journal that we're matching ourselves to. So does everybody know what Geophysical Research Letters is? Have you ever heard of that journal? Okay, so the American Geophysical Union, some of you have probably heard about people going to AGU in December. That's a big meeting. The American Geophysical Union is, I think, the biggest geophysical club. I guess they probably would prefer to be called a union or a society, but whatever. It's a club of students and scientists who are interested in geophysics or geology, earth sciences broadly. There are about 60,000 members worldwide, and it is American, so it's sort of centered in America, but it has lots of international participants as well. One of the things they do is they run these big meetings. Another thing they do is they give out prizes, which sometimes you'll hear about somebody winning an AGU medal or something, or becoming an AGU fellow. So that's like a nice thing. And then the last thing they do is they run journals. And they run a lot of journals. So the Journal of Geophysical Research, which has an oceans and atmospheres and a planets and a solid Earth branch, like there are multiple of those. But their kind of highest profile journal, which is also the shortest in terms of page length, is called Geophysical Research Letters. And the they break up things into what are called publication units, 12 publication units, and that's the page length that we're going to use for this class. So a publication unit can either be a figure or it can be 500 words. So if you add a figure, you have reduced the number of words that you get. If you add a lot of words, you can run out of room for your figures. So it's a nice length. You probably won't feel the enormous pressure to stick in that length unless you're somebody who likes to use a lot of figures or a lot of words. This is sort of the length. It's a comfortable length for what we've been doing, how big these papers are. The main thing is that it's meant to focus your mind on, in a short paper, what are the most important things to say. So you can't make 100 figures and just put them together with a title on the front, which is very tempting to do when you have a lot of data to look at. You actually have to distill a little in both the word side and the figure side to make it squeeze into that size. You definitely do not have to fill up all of that space. If you feel like you've said what you need to say, just stop. The reason why I chose this is partly because I don't want to read 70-page long papers either, and I know you don't want to write them. Like this is a nice concise length because it makes it a bite-sized package. So it's similar in length to Nature, Science, physical review letters. A bunch of other unions other than AGU have a short submission length, and they're kind of the highest profile papers because if you have one good idea, this is the right size to fit it in. If you have 10 good ideas, you need a different journal. But for one really good idea and you want to just explain it well, this is the right size. So that's about what we're shooting for. And so when you think about how many ideas you want to test, you're thinking kind of 1 to 3. 3 is pushing it. So you're really only 1 to 3 big ideas, and then supporting that is all you need to have to fill this length of paper. Does that make sense to everybody? So you can actually make it look like one, like it looks in the journal if you use LaTeX, but you don't have to. Okay. All right, so here are some of the things that I know I will just comment on, but I'll tell them anyway. So if in most scientific writing, it's tempting to say, I measured this, or I did this, or I used such and such, or I got this data. Don't do that. It's standard to say the temperature was measured, not I measured the temperature. It's sort of a weird thing to do, and sometimes it gets very tangled. If it's really, really tangled up and you just can't figure out how to say it, then you can use this one. But typically you want to talk about the physical world, not your own role in it. It's sort of an illusion of objectivity. Is everybody, science is not actually objective in some sense because you're still making choices, but we all understand that. But this is an old-fashioned way of concealing that a little. Everybody's very quiet when I said the science wasn't objective. We can move right on past that. Okay, so second part. Don't worry in the first one that you didn't get as far as you wanted to. This is part of the process. You may have produced a lot of information and you do not know how to tell a story that connects that information. You may have not produced much information at all and you have to tell a story with very little information. All of that is expected. This paper is the one where we're really learning the process more than we have a clear story to tell because you're just getting introduced to the concepts we need. By the time we get to the next paper, you're going to be using stuff that we've talked about in class directly into the paper in a very clean way. And so there will be a more coherent story to start with. It'll make more sense. Does that make sense to everybody? So don't get terribly worried about this, but we do need to go through the process once. I have tried multiple times teaching this class to delete the first paper and just go straight to the important paper, the second paper. It never works. The second paper becomes the first paper and then nobody knows what to do in the second paper. So this is the paper where we don't know what to do on, but we have to do it because the next paper we want to know what we're doing. Okay, so think about it that way. All right. This is an important piece of what the story is. You should be looking for kind of 5 to 10 things to talk about in your bibliography, to have in your bibliography. You don't have to understand those papers in great detail, but they should be something that's relevant to what you're doing. So if you find the best kind of paper to cite is, here is a review paper describing the currents in the region that I'm talking about. You do not have to understand everything about that paper. You can take a figure out of that paper that maps the currents and put it as your opening figure just to get people squared away. Or you can just leave it to the reader to go to that paper if they have more questions. But that's a really good one. So you definitely want to find at least one like that. Maybe two like that is good. An old one and a new one or something like that. Or a satellite one and an observations from a ship one. Something like that. That's a nice place to start. Then you want to have one or two that maybe ask a question that you're interested in engaging with. Like, is there a trend in salinity in this region? You can find a couple of other papers that talk about that using similar data to what you used, and now you have a longer data set, say, or using different data than what you have, and you're just complementing them by taking your approach. Does that make sense? So there's kind of two papers like that you find, and then there probably will be others that as you're looking through those four, you see them mentioned, referenced, this, that, and the other, and you might want to bring those in to kind of round out what the field looks like. Okay? For a real research paper, it'd be more like 30 to 50, right? So it would be a more extensive search. But you really don't want to get into the business of having just one, and it's okay to use the textbook, but if you use the textbook and it's the only one, you're definitely not engaging enough with Google Scholar and looking in the literature. Everybody on board with that? And this will also be a part of the learning process. It's hard to figure this out until you've done it a few times. Okay, are there questions about all this stuff now as you think about it? I hope everybody's kind of starting to have some pieces in mind. Yes? No? You haven't thought about it since the plans were due. You just completely blocked it out. Yeah. So there's plenty of time left. From plans, everybody had done a good job at getting started and starting to have some concrete ideas. But there's more that needs to get done before you're ready to write it down as a paper. And I would strongly recommend that you do little bits and pieces, a little each day, rather than try and do it all in a big push at the end. That essentially never works. So if you do a big push today and you don't finish it, it's not a big deal. If you do a big push on Saturday morning, you're not going to be able to finish it, or things will break and you won't know why, and you won't have time to let it cool down and come back to it. Okay? Yeah.
This is kind of a specific question, but is what directions are V current and U current? Because it didn't really say in my data set which directions it were, but
yes,
it just says that.
It differs. It's a worse story than you would imagine. It differs depending on which version of the Echo model you are using, data sets you're using. There's one called the lat long, and that one has east, so at ADVE and ADVN, and I believe that U and V are oriented, so U is in the eastward direction and V is northward. And as the grid moves, that's kind of a different direction a little bit. In the NC Tiles version, which we have not talked about yet, but there's a version which is the native one that the model got ran on, which has the Arctic, and it's actually like a polygon covering the surface of the Earth with 13 different faces. Then the U's and V's are oriented along the grid, but the grid isn't necessarily oriented east-west, north-south. Sometimes it's in a different direction. So I have tried to make that easier for you by doing I have the interpolated file, which is called interp underscore something else, and the lat long one. And so the interp one does everything that the model does, except it ignores the part where the coordinate system gets curvy. So it just chops off the North Pacific, North Atlantic, and the Arctic. The lat long one extends up into that domain, but not all the variables make sense because it's not the grid that the model ran on. It's like an interpolation onto latitude and longitude lines. So depending on the application we're using, you might choose to use the lat long or the interp, or if you're really determined, the NC Tiles version, which has this crazy grid system. So, but that's the difference between those three. And typically the east-west-ish direction is the U velocity. the north-south-ish direction is the V velocity, but sometimes east-west is not actually east because the grid is rotated around. Does that make sense?
Yeah, and you said east was positive and north was positive?
Yes, yeah, that's right. And you'll also find as you're reading papers maybe that oceanographers and atmospheric scientists do the opposite thing. So oceanographers like to talk about where the current is going. So they would say eastward or an east current, northward or a north current. Meteorologists like to talk about where the wind is coming from. So a westerly is coming from the west to the east. So it's very confusing at first. But the way to remember is if you're in a boat, you go in the direction of the current. So the thing you want to know about the current is which direction it's carrying your boat. If you're thinking about a weather system coming in, you don't want to know where it's going, you want to know where it came from, because if it's like a polar vortex, it's a northerly wind. It's coming from the north, it brings cold air. Does that make sense? And the vertical coordinate switch, which is also complicated in a way that we're not, well, we actually will talk about it. We're going to start to talk about the hydrostatic balance a little bit today. Yeah.
So I tried to use a newer version of the equal model.
Mm-hmm.
Okay.
It is okay. There is a release 3.
Yeah.
You can get the netcdf files the same way. The only thing is they will not have the lat long version. I'd have to give you code to convert to lat long. But if you are in the southern hemisphere or like up to I think 60 north or so, then their grid is the same as the lat long grid.
I was trying to use the climatology kind of data, and I thought I was using the lat long by just kind of reading through what the lat long. They have a grade of lat long.
They may have converted it to lat long, but you have to be very careful about whether, like, what direction the velocities are. Are they actually east-west, north-south, or are they grid or aligned?
Okay.
And did it all come down as one data set, or it came down as 13 different netcdf files, or something with a large number?
So they have climatology and the netcdf, like the net grid
Yeah.
thing.
Yeah.
Make them separate as different files.
So they have already pre-processed it the same way that I have for the release 2. So the climatology should be the same. Does everybody know what a climatology is? This is always something that comes up. So what's the difference? Okay, what's the difference between weather and climate? One is long-term, one is short-term. So a climatology is seeking to describe only the climate, only the generic statistics, not the variations from day to day or month to month. So an easy way to make a climatology, say you have 20 years of data, you don't give 20 years of January, February, March, April, so on for 240 months. You take an average over all the Januaries, and then an average over all the Februaries, and an average over all the Marches. So it's not actually a time series that ever occurred in the real world. It's like a typical month by month, or you could do a climatology day by day, and it would be the typical January 13th or whatever, February 7th, whatever. You could do it like that, but the idea is you're eliminating the weather by averaging many years together. So a climatology is that. So it's not a time series, and what you can't do with a climatology is look for a climate trend, for example, from over that 10-year window. It's in there in the sense that you use the same data to generate that, but exactly what gets removed are those long-term trends. So climatology tells you about the typical year, not about the specific years that the data was collected in. And it is also possible, one last piece is, a climatology is not actually a physically realizable state of the world. So you might go to examine the momentum balance in a climatology and find something that does not make sense, because the different terms in the momentum equation are from different years. And when you add them together, you might actually find that your fundamental physical principle was violated. And so that's a tricky part of working with climatology. It's rare, but it kind of exists in the real world. Does that make sense? It's an average over multiple years, so it's not the weather in a climatology, the data in a climatology is that never occurred in the real world. It's a synthesis of multiple occurrences. So as long as you keep that in mind, it's fine. Do you have a question?
How would, if we wanted to find the original data, then how would we find that?
So for the release 2, I have the monthly data, I have the climatology data, and I think I have the all-time average data. So there are 3 different data sets. So the monthly data is just month by month by month over the 20 years of the run. The climatology is 1 year, that's averaging 20 months onto each. And then the total average is, don't even bother about what month it is, just average all the data into one file. That one is obviously the smallest. It's 240 times smaller than the monthly output. So if you're struggling with the quantity of data, you can switch to a climatology or to the total time average. And for most projects, it doesn't really matter. It just depends on what you're trying to do, whether you want the time series or whether you're okay with just, oh, this is a typical year. I'm just interested in the summer versus winter temperature anyway. That's fine. Does that make sense? Yeah.
So under what situation do we prefer to use the latitude, longitude data, and under which situations we want to use the interpreter data?
So the latitude, longitude data is the easiest to use. And most of the time, if you just wanted to make a map of what the temperature was on a particular month, just grab the latitude, longitude data and use it. If you are trying to balance the terms and the equation of motion, which we're going to get to, then you might not want to use the latitude, longitude one because they won't balance as neatly as they would if you're using the native grid of the model. So that's the advantage of the interp one is that it looks like latitude, longitude, just not over the whole Earth, but it is also the native grid of the model. So as long as you're using the interp, interp's the right one? Yeah. As long as you're using the interp, everybody is actually oriented in latitude, longitude, and it is also the native grid of the model. It just deletes the part of the Earth that isn't latitude, longitude in that original model. Does that make sense? Okay. Any other questions? Oh. When we get to reviewing, there's a funny numbering system, which as you're reviewing, you should give everybody a number. One of them is a letter grade that's for presentation, and one of them is a number that's for quality of the science. Those are 2 different things. So if it's really well written, but the science doesn't make sense or it didn't work, then you might give it an A4. And if it's really, really good science, but you had a hard time figuring out what they were talking about because everything was mislabeled and the sections all didn't make sense, then you might give it a D1. Typically, we're going to be having things that are like B2, B3, B1, A3, whatever, in that territory. And I put these into a formula of like what the overall grade is, but my grade sort of overweighs the other ones. So, but the nice thing about this is it is sort of a summary at the end, like you're trying to get a consistency between your grading and the comments you're giving. And if you give a really low grade, you should give a lot of comments, like what needs to be fixed. And then if you give a really high grade, you actually may not have many things that you're suggesting to be fixed. What we're trying to avoid is not saying very much about the paper and then giving it a terrible grade, which is not a satisfying combination. So you need to have reason why you didn't like it, or some reasons why you did, and you can tell them both positive and negative comments. Does that make sense, everybody? Okay. Oh, all right. We'll come back to this next time. Or, well, I don't know. We'll come back to this next time. I want to get on to the other stuff. All right. Okay, we'll skip the Hulk for now. All right. Okay, so last time we talked about using an estuary as a control volume. And we have all this funny, it occurred to me that I didn't say this out loud, even though I was thinking it in my head. We're using a lot of calculus and integral calculus, but really all we're doing is using the divergence theorem. What we're going to get to is we're just going to say, once we're comfortable with like how a grid cell works or a control volume works, we're not going to do this fancy integrals anymore. We're just going to say, oh, I've got the divergence of something. I'll just think about the flow in and out of the box. I'm not going to worry about what's going on inside the box. So this is a lot of mathematical machinery to convince you that the idea of a control volume, whether it's a grid cell or an estuary or the whole Earth, is a useful thing to think about. But to some people, this is totally opaque, and that's fine. We're not actually, you don't have to be responsible for this step on your own. You just need to understand that there is a mathematical basis for breaking up the ocean into grid by grid, and that you would be able to take a differential equation and express it on all the grid cells using this kind of math, even if you didn't want to do it yourself. Does that make sense to everybody? Okay. So what were the conclusions? We figured out that when you balance the volume, that teaches you some things, but if you balance the volume flow and also the salts, you actually start to get a sense of what's going on in the basin. Is it mixing a lot? Is it just a fresh layer that slides on the top with relatively little entrainment of salty water as it goes? And we saw that the Black Sea was of the second kind, the Mediterranean was of the first kind. And we kind of hinted that, if we were talking pollution, it would be we could do a similar calculation. Salt wasn't the only thing. And today we're going to talk about energy, so heat. And the same thing occurs. We could do a budget for heat, just like we did for salt, or just like we did for fresh water. Okay? So, where does the heat on the Earth come from? The sun, almost all of it. There's a little bit of heat left inside the Earth from the formation of the planet, and there's a little bit of heat left inside the Earth from radioactive decay. Those are on the order of milliwatts per square meter. This is on the order of 1,000 watts per square meter. So it is, most of the heat is coming from the sun and going back to space, and that's the budget we're normally thinking about. Okay? Where does the sun shine the brightest? At the equator, or at noon, either way, when the sun is directly overhead. So one way to think of it is the energy flowing in a beam, if it passed through a surface, it would be the same amount of energy regardless of where it's going. But if it comes directly in, it actually delivers more energy per unit area than if it comes in like this. This is a bigger surface than this is. Does that make sense to everybody? So there's a factor of cosine of latitude involved, which is like, that comes out of just the geometry of how big this area is versus how big this area is. Okay? Plus, how long is the polar night?
6 months.
In the wintertime hemisphere, there's just no sun at all for a long time. So the length of the day is also kind of a factor. This is instantaneously true, but this side of the Earth is at night, this side is in the day, and depending on the tilt and what season it is and how it's rotating, you might end up with a very short day or a very long day. And so a big part of this is the length of the day is a big part of the net insolation, which means the incoming solar radiation is compressed into insolation. So that's a funny word. Okay. So, but you might think of power or energy per unit time, so watts or joules per second per length squared, per area, per meter squared. Okay, the units are usually in terms of power delivered per meter squared of the surface. Okay. So the net piece is that there's less power arriving at the poles. Okay. So there's energy coming in and there's energy going back out. And last time we talked about the black body radiation. So the fact that everything that has a temperature that's above absolute zero emits some amount of radiation. And we know in the end, remember that thing with the clouds and the albedo and the bouncing and whatever? In the end, that's got to balance back out what's coming in if the Earth has a stable temperature. The Earth doesn't quite have a stable temperature, but it's warming relatively slowly. So stable temperature is still close enough to what goes on with the energy budget, right? How much is the Earth warming? This is a fact that all our scientists should know. How much warmer is it now than it was in 1900, roughly?
2 degrees Celsius.
Yeah. 1 to 2 degrees Celsius is kind of ballpark. Like 1 degree in the past, and we're looking like we might get up to 2 degrees, 3 degrees, 5 degrees, depending on what we do by the end of this century. Okay, so that's a ballpark range. Okay, all right. But so if more energy is coming in near the tropics, or near the equator, and there's less energy coming in out there, and if the temperature of the planet was totally uniform, it would be emitting back at the same rate per square meter. It's a little bit cooler at the poles than it is at the tropics. But if you plot the outward going and the incoming, it looks like this. So the incoming is the red one, and the outgoing is the blue one. And this is averaged over year after year. It actually doesn't look like this in the wintertime. The winter hemisphere has a bigger deficit, and it actually goes kind of all the way there. So this difference in energy per unit area arriving, what would that do if nothing else happened? The temperature would decrease until the blue one dropped down and maxed the red one. So if the Earth was a rocky planet, or the Earth with no atmosphere, or the Earth was a big metal sphere, the blue and the red would pretty much line up. So the equator would be much warmer than it is. The poles would be much colder than they are. But that's not what happens. What happens is that there's heat transfer from the regions that receive a surplus to the regions that receive a deficit. How do you move heat like that from latitude to latitude? Currents in the ocean? A warm current moving poleward, or a cold current moving equatorward, or the exchange of those two is a heat transfer, or warm air moving poleward, cool air moving equatorward, or most important, so there's a third one, which is moist air moving poleward and liquid water moving equatorward. There is energy in evaporation of heat of water. So if it goes in the vapor phase one direction and the liquid phase another direction, that's like having hot stuff go one way because it has extra energy being vapor, and cold stuff go the other way because it has less energy being liquid. It's true also of ice. If you had ice going this way and liquid water coming back to replace it, that's also a heat transfer, but it's a very small one compared to the others, okay? So there's three different ones. There's ocean currents, warm currents moving one way, cold moving the other, warm air moving one way, cool air moving the other, water vapor moving one way, liquid water moving back. Those three together are about equal parts of this heat transfer. And so sometimes you'll hear that the atmosphere carries twice as much heat as the ocean, or 3 times as much, and it's because they're putting that water vapor part together with the warm air part. And then the ocean is the last bit. But it's really kind of 3 relatively equal units is the easy way to remember it. Okay? And so the energy transports from equator to equator.
The first law of thermodynamics. Heat is work and work is heat.
Heat is work and work is heat.
Very good. The second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you'd far better not.
You can try it if you like, but you're far better not.
Cause the cold in the cooler will get hotter as a ruler.
Cold in the cooler will get hotter as a ruler.
Because the hotter body's heat will pass to the cooler.
Because the hotter body's heat will pass to the
First
cooler.
law, heat is work and work is heat and work is heat and heat is work. Heat will pass by conduction and heat
will pass by conduction and
heat will pass by convection.
Will pass by convection.
Heat will pass by radiation. And that's a physical law. Heat is work and work's a curse. And all the heat in the universe
All right.
is gonna cool down.
Okay, sorry. Anyway, is he gonna play it again? No, I don't think so. Okay. So that funny little song is about the first and second laws of thermodynamics. The first law is work is heat and heat is work. The second law is heat doesn't go from the cooler to the hotter. It tends to go from the hotter to the cooler. So we'll get more into those. Both of those are essentially where potential temperature comes from. The first one is a conversion between units of energy and temperature. So that's part of what we're thinking about. The second one is about the transport of entropy. And so potential temperature can be thought of as both a measure of entropy and a measure of energy, because it's in simple fluids. Okay, but the important part at this point was heat can move by radiation. We've been talking about that. Sun coming and going and infrared going in and out. Heat can move by convection. So that's hot air going one way, cool air going the other way. That's convection. And then the last one was heat can move by conduction. And that's just hot stuff hooked to cold stuff and kind of diffusion along. Okay? So those are the three ways to think of it. In the atmosphere-ocean system, convection and radiation are totally dominant over conduction. In ice, conduction can be really important. And in land, conduction can also be really important. Yeah?
Can I understand like the mixing of water as convection?
No, it's more convection. This is more the mixing part. This is really like molecules talking to molecules. So this would be like diffusion in water, or the diffusivity. And the ratio of this one to this one is called the Peclet number, and that's actually a very large number in all natural flows. Okay, right. Okay, so when we're thinking of the energy budget, we are adding some here. We're adding some there. We've got flows that are going by convection, and also latent heat transport. So that's the part of the vapor coming back as liquid water. That's a different flavor of convection, essentially. And we're trying to balance out this deficit and excess of energy. So that's what makes the winds and the currents go, is essentially this. But if this didn't work, there would be no wind, there would be no ocean currents. Okay, so let's take a look at what it looks like in the real world before we get to the consequences of what the temperatures look like in the real world. This is the one we showed last time. This is the air-sea flux of energy. So here, blue is showing where the ocean is losing energy to the atmosphere. So that's a warm current, the Gulf Stream. It tends to warm the atmosphere above it. And yellow is where the ocean is being warmed by the atmosphere, or gaining energy. It could also be getting warm from the sun. This is the net heating and cooling of the ocean side. It doesn't really distinguish between radiation and air-sea latent heat. Air-sea sensible heat, that's the hot air, cold air part. So, does this look like that deficit excess picture? Kind of. There's an excess of heating in a band in the tropics, and then there's energy coming back out farther away, and this background blue that looks kind of vague is actually a negative number. So the ocean is warming on net in all of this background blue as well. So it is being heated at the equator, and it is cooling off away from the equator. So we think that the net transport of heat has to go which way in the ocean? From yellow to blue, or from blue to yellow? From yellow to blue. From the places it's getting warmed to the places it's being cooled. That's the way it's got to work if the temperature's to stay balanced. And these little arrows are in fact telling you which way the heat is going. You can see that in the Pacific, except for up there, which is crazy, it looks sort of like what we'd expect, that it's going away from the tropics. Relatively symmetric, at least order of magnitude symmetric between north and south. In the Atlantic, something crazy is happening. It's going north everywhere. It's not going poleward. It's going polarward in the northern Atlantic, but it's actually going equatorward to the South Atlantic. And this is something called the AMOC, Atlantic Meridional Overturning Circulation, that's driving this. We're going to talk a lot about that. It's a weird oddity of how the Earth works. In the Indian Ocean, it's going away from the equator toward the pole, but you can't go north out of there. There's no water. I mean, you could go through Suez Canal, I guess, but not very effectively, right? Okay. So how could we measure that? We can measure pieces of it by satellites. The radiation part, for sure. We can measure the incoming radiation. We can measure the reflected off the surface. It's a little complicated because the atmosphere is absorbing and so are the clouds. We could go down and do the kind of the same thing. We could put a radiometer that's looking down at the ocean and a radiometer that's looking up. And we could figure out what's happening. Like, what's lights coming in, lights going out. That tells us about the radiation part. That's essentially how it's done. Those instruments are expensive, and they are definitely not global. So you have to go everywhere in the world and use one to really do that, which is extremely complicated. What about the other parts? What about the energy exchange from warm ocean to cooler atmosphere? So basically, we have laws that tell us how much energy should go if we have a particular temperature difference. And so we go measure the temperature differences. We go out in boats and we measure the atmospheric temperature, we measure the ocean temperature. We can also do that from satellite to some extent, which is slightly different from the first calculation. But that's one of the pieces. That equation is actually not as simple as that. It also depends on the wind speed. Because what really happens is that if you put warm ocean next to cool air, a little layer of the surface of the ocean cools off and a little layer of the atmosphere warms up, and then it just sits there. It doesn't really do anything else. So you need to refresh it and bring back in more cold water from below, more air to be warmed up, or more warm water from below, more air to be warmed up from above. So it depends also on wind speed. And then it depends on which one is the hot one and which one is the cold one. Because as we just learned from the song, the heat is going to go from the hot one to the cold one. But sometimes, in summertime, the atmosphere is the hot one and the ocean is the cold one. And in wintertime, it's the other way around. So they're coming and going and coming and going. So it is a very messy statistical problem to try and get at that part of it. And then there's the evaporation law, which is even more complicated than the air-sea heat law because it depends on the temperature difference and in the wind speed and also the atmospheric humidity. So all of these pieces go together to make this map. So this map is not very certain. It's one of the more difficult things to measure about the Earth. Okay, but where does the energy, is there any other appreciably large source of energy for the ocean? Does everything come through the surface? There's geothermal. So these are in watts per meter squared. So we're talking about 50, 100-ish, or minus 50. And the geothermal is about 50 milliwatts per meter squared. And it's not very, it really much is just on the mid-ocean ridges. So yes, there is geothermal, but there's not a whole lot of it. So first order, this is where all the energy comes from. So if there's an imbalance here, what happens? What could we detect that might be easier than measuring the transfer from atmosphere to ocean? Suppose the fluxes change for 10 years. What should we be able to tell?
With would that affect the currents?
It'll affect the currents, but even before it affects the currents, it'll just change the temperature. If you go out of balance for a while, it's going to start warming up. So the way we measure the long-term changes in the fluxes is not actually from the fluxes themselves. It's from detecting temperature change in the ocean. And the same is true of evaporation minus precipitation. It's very hard to measure those fluxes. It's easier just to go measure changes in salinity. So if evaporation is dominating over precipitation, the salinity will be changing. So this is kind of like the budget exercise we're talking about. Is the water getting saltier? If so, that implies that there's a local imbalance, and then the current is taking it away, the saltier water. So that concept of like, maybe you can't measure all the parts of that budget, but you know that budget is satisfied. So just like we have with the estuary, it would have been very hard to measure the air-sea fluxes into the estuary, but if we knew the inflow and outflow at the ocean mouth, and we knew all the rivers coming in, we could figure out what the E minus P was, because we had those constraints of the rest of it. So the idea of a budget is to employ some constraints to make the things that are easy to measure inform you about the things that are hard to measure. Yeah?
Do you think the glacier melt is a negative influx source?
So the glacier melt, so glaciers melting comes in more or less at freezing temperature. So it is colder on average than the ocean. So in some sense, yes, it's tending to make the ocean colder, but it's not a very large source of energy. There's just not enough glacier. Like, even if all of them melted all at once, it still wouldn't be a very large amount of water. I mean, it's a large amount of water for sea level rise. We would care a lot. The sea level would shoot up, 80 meters. But 80 meters versus the 4.7 kilometers of the ocean is actually not very much. So the total energy in the ice is a relatively small comparison to warming and cooling the whole of the ocean. Does that make sense?
Even like local impact,
Oh, so you want, yeah, is there a little local signal here? Yeah, I mean, you can find places where it matters, like in the fjords and where the glaciers here are dumping out. Yeah, you can see the signal of the cold water coming off the melt. And you certainly can see it in salinity, because the fresh water has essentially no balance. The cold water, if it's near the surface quickly, it changes its temperature by mixing, but also changes its temperature through exchange with the atmosphere. So it's hard to see that signal, but since there's no source of salt, the fresh water persists for a while. Okay, so another way to get this is to do what we always do with weather models and then figure out what the imbalance was. So the atmosphere also has to be consistent in its energy. So we can go up on a satellite and observe how much energy is coming in and figure out how much of it is absorbed by the atmosphere. We can figure out, since we're right at the top of the atmosphere, how much is going out from the top of the atmosphere. And so we can make the net warming of the atmosphere. So this is pretty easy to do because the atmosphere is transparent, so we can see what's going on. And the timescales are pretty fast for mixing, so everything kind of equilibrates pretty fast. And the satellite isn't remote from the surface of the atmosphere. It's right there at the surface of the atmosphere. So the whole signal is right there ready to be measured. So this doesn't quite balance out. There's a little bit of it that's the transport in the atmosphere, and we can also measure that directly from knowing the winds and the temperatures and the humidities. But there's still a little bit left over. So where does that little bit left over go?
You mean the net energy budget of
Mhm.
atmosphere doesn't concern?
It doesn't quite close at the top, plus the transport.
Temperature has to go up.
It's not quite that the average temperature has to go up. There's one other thing that the atmosphere can do, which we've been talking about all along. So if you take all of the stuff that's happening just in the atmosphere from above and the lateral transport, there will still be leftover bits of energy. Some places will have a convergence of energy that has no nowhere to go in that budget. It goes down into the ocean. So actually the best way to, or it has traditionally been the best way to measure how much energy arrives in the ocean is by figuring out what the residual is of the atmosphere. You add up all the pieces in the atmosphere that are easy to measure, and whatever's left over must be going to the ocean. And so maps like this can be formed just from the residual of the atmosphere. And in fact, I think that one is. Which one is this? Yeah, this is NOCS. So yes, that's a residual of an atmospheric model. Okay, so here's our excess deficit map. Another way to think of this is how much transport you need. So it's like the derivative. This is the derivative of a transport from equator to pole. And so here's the atmospheric transport in the northern hemisphere going north, the southern hemisphere going south, so going poleward in both directions. That's this. Oh, sorry, let me break this down a little bit. The atmospheres are the dashed lines, and the total, which is essentially the derivative, the integral of this line, how much you need to do is those. And so from that residual process, you can figure out what the ocean transports are. And so this is two different estimates using two different atmospheric models, taking the residual, summing them up, and figuring out how much energy is going in which basin in the ocean. So the total looks like this. It's about 1 petawatt of transport to the poleward total. And here's the Atlantic, which is north everywhere, about 0.5 petawatt. Here's the Pacific, which looks like the total, just smaller. And then the Indian goes this way. Does that make sense to everybody what this is? This is just the meridional transport broken down latitude by latitude. Okay? And you can go further and break it down into whether the air-sea exchanges, how they're exchanging. So sensible is hot air touching cold water or vice versa. Long wave is the radiation coming out of the ocean minus the radiation from the heat of the atmosphere going in. Short wave is the sunlight. The latent heat is the heat having to do with evaporation. You add them all up, and this little net profile is essentially the excess deficit map that we just looked at before. Okay? So, super complicated. Each one of these requires a different instrument to measure it. So if you're gonna measure these one at a time, it's pretty hard to do. So back to that same basic point.
So the very first energy flux of the ocean was derived from this map instead of the kind of measuring the heat flux directly from the ocean.
So yes, people had done this point by point, but they didn't know what it looked like globally, because you have to actually go everywhere in the world for every season, which is hard to do. So instead, the first maps of the global heating of the ocean came from the residual of the atmospheric models. And all of this is relatively recent. I mean, this whole concept of this stuff is like only in the last 40 years that they've figured out how to measure this at all. So this is kind of like a bit of the story of climate change, essentially. Okay, you can do the same game for freshwater as we talked with last time. So when we're thinking of this as an estuary, we can think of the freshwater budget, we can think of energy budget, we could chop it up basin by basin, we could chop it up latitude by latitude. All of those budgets are parts of the game that we're on about. Okay? All right. And then it is also variable in time. These are just the standard deviations of all those fields. And it's a mess to figure this out because there's storms and there's like cloudiness and all kinds of stuff is changing this. So it's really there's a whole group of scientists who just spend their whole lives trying to do this and trying to measure this accurately. So it's a really complicated problem. All right. Okay, so this starts to touch on how ECHO comes into this game. So what does ECHO do with its freshwater budget, its salinity budget, its energy budget? We kind of talked about it from the perspective of one grid cell. But is that fundamentally different from the whole ocean? Not really. Every grid cell in the model has a budget. If you hook them all together, there's a budget for the whole thing. And the model conserves energy, and it conserves salt, and it conserves fresh water. So it just does this all the time. An echo is a data assimilating model. So that means that when there's an observation, the model is tweaked a little to make it closer to the observation. So even though they're not observations everywhere in the model that we're looking at, it's as close to observations as we should expect it to be based on the uncertainty in the observations. So that whole idea of let me figure out the question you're asking based on the behavior of a model that is conserving those things is called an inverse model. So you're asking what the forcing was at the surface, what the transports were, in order to make it more like the observations, rather than saying, here are the transport, here's the forcing, here's the currents, now what's the answer? That's a forward model going in that direction. Echo is an inverse model in the sense that it pushes itself toward the observations and works it back and then changes the fluxes to make it all self-consistent. So that's part of the understanding of what echo is. Does that sort of make sense to everybody? So if you go and measure the fluxes in echo, the heat transport, latitude by latitude, it should look an awful lot like the observations. And it should certainly conserve heat to the level that it's supposed to its numerical accuracy. Does that make sense to everybody? Yeah.
So how does it resolve the small scale stuff that observations don't have?
Right. So it has a lot of parameterizations in it, like diffusion and parameterizations of the air-sea fluxes. And what it does, it actually is kind of an inverse model and a forward model together. So they run forward, they compare the observations, then they go back and they change all the small scale stuff and the air-sea fluxes. They run forward again, and then they go back and then they tweak it. And they run through it again, and they go back and they tweak it. So I don't remember what iteration this version of the model is. I think it's like 37 or 47. So they've done that 47 times. They've simulated this, tweaked it, and gone back to the beginning. So the nice thing about it is that they don't violate energy conservation or anything. It's still a forward model running, conserving based on its surface fluxes, but the surface fluxes are tweaked where the observations allow in order to make the model closer to the data. Does that make sense to everybody? Another way to do data assimilation would be just to say, wow, there's temperature here, I just observed it, I'm just going to change that grid cell's temperature. The problem with that is that it doesn't conserve energy anymore because you just made up energy to make that thing warmer to match the observation. So this backwards and forwards stuff helps make the model self-consistent with these kind of budget ideas. Yeah, so yeah.
I'm just curious, how does the tweaking process work? Is this done manually or? Is
No, it's not done manually. It's done automatically with something called the tangent linear adjoint. So it essentially propagates the mismatch backwards in time based on a version of the model that can be run backwards in time. So it runs forwards, it sees the mismatch, and then it backward propagates that perturbation back to the source and collects it, and then runs it forwards. So it's kind of a math trick. It's an interesting math trick, but that's actually all explained in the appendix of Wunsch if you want to get to know more how it's done. All right, cool. This is another observational estimate for the volume transport, so that's the salinity freshwater part. It's just as complicated of a story thinking there. And this is basically water flowing from rainy places to water flowing to dry places. And you got to make it work, otherwise the water would be changing. So that's part of the story too. Okay. So the motions of the atmosphere and the ocean are part of the meridional redistribution of heat that rebalances the radiation imbalance latitude by latitude. The ocean overturning, gyres, the atmospheric cells, all this motions that we're going to be talking about are all contributing to this story. And estimating both the air-sea fluxes and the fluxes within the ocean is tricky, but it's an important part of the understanding the ocean and climate change. Is everybody on board with all those pieces? Okay, so let's talk a little bit about heat capacity and water and temperature and potential temperature. We're going to come back to this next time, I think, but let's give a flavor of where it's going. Okay. So Earth is special. One of the reasons why is because water is special, and there's a whole lot of water on Earth. So water is special because it has enormous heat capacity. We talked about this last time. So, but water is also special because it varies in density. So the oceans are stratified by density. They're less dense at the top, more dense at the bottom. In old-fashioned things, they would say it's rarefied at the top and dense at the bottom. We tend to say it's light at the top and dense at the bottom, but light isn't exactly the antonym of dense, so that's a little weird. Okay, anyway, and then there's pressure variations, and most of it is hydrostatic. So hydrostatic is basically it's the accumulation of pressure because there's stuff on top of you. So as you move closer to the Earth, there's more and more stuff on top of you, and so your pressure goes up and up. And we're going to see that in equation form, but that's a useful way to remember. So we're going to talk a little bit about seawater's heat capacity, the equation of state. This is the thing that relates pressure, density, temperature, and salinity are related together by the equation of state. So the thermodynamic equation that and you may have heard of the ideal gas law, which does that for ideal gases like nitrogen. It's way more complicated for seawater, but we can approximate it pretty simply by just saying that when it gets warmer, it gets less dense. When it gets saltier, it gets more dense. When it goes up in pressure, it gets more dense. So that's close to what it is, close enough for most of our purposes. Okay? All right. Here's a bunch of things that I'm not even going to talk about, but there's a lot of strange words that come into this. So remember this movie that we saw with the fast atmosphere and the slow ocean? One of the reasons why it's fast and slow is because of the heat capacity is so different. So the energy that needs to get moved around in the atmosphere makes stuff move really, really fast because per unit mass of the atmosphere, it has to have a whole lot of temperature change to move some energy. Per unit mass of the ocean, you don't need to move as fast to carry the same amount of energy for the same temperature change because of the heat capacity. And another way to put it is, and then in addition, the atmosphere is less dense than the ocean. So the ocean is heavy per unit volume, so you don't need to move a lot of volume to get the same transport of energy. And one of the reasons why is because of these little hydrogens and oxygens. We talked about this last time a little. So the oxygen with two hydrogens on it, that's water. And the hydrogen, oh, I'm going to get this wrong. The hydrogen the electrons tend to hang out on the oxygen, and so there's a little bit of a polarity in the net distribution of charge around this guy. So the hydrogen side is a little bit towards the positive, and the oxygen side is a little bit towards the negative, which means that a hydrogen tends to be attracted to a neighboring oxygen, just a little. Not enough to break the bond between the hydrogen and the oxygen, but enough to have the molecules like to orient themselves next to each other. And if you try and pull them apart, they resist because of that same polarity. And so water has a very high heat capacity because of these polar bonds between the different molecules. So we can think of that in terms of the sensible heating. So when we're a change in temperature, there's this thing called the specific heat. So a change in temperature times the specific heat gives you an amount of energy change required to change it. Or since more stuff takes more energy to heat up, we frequently do this with a lowercase cp. So this is the specific heat capacity. This is the heat capacity. This is the heat capacity per unit mass times the mass times delta temperature. Okay? So water vapor and ice have about half a calorie per gram per degree C is this guy. Air is about a quarter of a calorie per gram per degree C for this guy. And liquid water is about 1 calorie. So heating, it takes 4 times as much energy to heat a gram of water 1 degree C as it does for dry air. And it takes twice as much energy to heat liquid water 1 degree than it does to heat water vapor. Does that make sense to everybody? Well, I mean, it doesn't make sense. These are things that you should know about how water and air works. Okay. So if you want to do this, you can convert between, oh, and also calories are like old-fashioned. Now people like to use joules, so there's only one unit of energy. That's the conversion factor, 4.816 joules per calorie. And calories that you eat are actually not calories, those are kilocalories. So if you want to figure out how much food you have to burn to heat up water, you can do that, but remember that those calories are kilocalories. So when you eat a muffin, it's like 480,000 calories of this variety. So when you eat a muffin and then spend all day exerting watts doing things, you can you can take that out. Okay, here we go. Then there's the other kind of heat, latent heat. So latent heat is the energy that comes out of the closet when you change phase. So this is the energy that is stored in the phase of the molecules. So changing from solid to liquid requires energy. Changing from liquid to gas requires energy. Okay? And it's latent because it's there in the phase, but it does not affect the temperature. Okay? So it takes about 80 calories per gram to change ice at 0 degrees C into water at 0 degrees C. It does not change the temperature, but it takes 80 calories per gram. So that's the same amount of energy as it would take that 0 degrees C water and heat it to 80 degrees C. So it's a huge amount of energy required to melt ice, but it is a truly huge amount of energy to evaporate. 540 calories per gram. So you can go from 0 to boiling more than 5 times over in the same amount of energy as it goes to go from 100 degree liquid to 100 degree gas. So this liquid gas piece, you might have noticed way back when on our energy little diagram. Look how big the latent is. That's, in some sense, that's a huge part of the exchange. That's the biggest exchange of energy between the atmosphere and the ocean. It's through evaporation of the ocean, turning into water vapor. That's where the energy is going. The rest of the only other big turn is the sun, which has nothing to do with the atmosphere. It just comes through the atmosphere and heats up the ocean. So it's a leading order of the energy budget of the ocean. As sun comes in, evaporated ocean goes out. Okay? And it's because that latent heat of vaporization is so large for water. And this is what it looks like when when you get fog on the water. That's like basically that's the process. Okay? All right, so if we look at an energy diagram of how temperature changes, so in units of heat on this axis, we can think of the 3 phases of water on that axis, and this is at room pressure kind of level. So if you start with ice at negative 40 C, and you heat it about 20 calories per gram, then you get to 0 C ice. And then it takes another 80 calories per gram to melt that ice. And then you have 0 degree water, liquid water. And then it takes 100 more calories per gram to get you to 100 C to get 100 C liquid water. And then it takes 540 calories per gram to evaporate that water and get to 100 degrees C water vapor. And then after that point, it's half a calorie per gram per degree C to go on. Does that make sense to people? So if you start out with ice, that's the way you melt. If you start out somewhere else, you can go up or down by heating and cooling, but when you go to these phase transitions, you'll just sit there for a while the energy is going into or out of the phase transition. So you don't immediately freeze to ice. You start freezing in bits and pieces, and then that ice is kicking out extra energy in order to redistribute it. And so it's a very complicated process here, and it's a complicated process here. Boiling is also really complicated, and because it's a heterogeneous, small-scale mixture process. But this is the way you can figure out, I mean, this is like the best figure of this variety I've ever seen, where you can think about how you jump back and forth between different temperatures and different phases and think of it all together. If the pressure is high, does this look the same? No. High pressure stuff resists. So is ice more or less dense than water? It's less dense because it floats, which is another weird thing of water. Other ices are more dense in the solid form than the liquid, typically. Not other ices. Other solids are, they tend to get less dense when they melt. Water's a weird one. But, so there is a resistance to forming ice at very high pressures because you need to expand, essentially. So you have your compressive work that you're working against to do that. Similarly, at very low pressures, it's quite easy to boil. It happens at a much lower temperature. I think it still takes the same amount of energy. There's still the same amount of energy difference between the water vapor and the liquid water, but it happens at different temperatures. So when we think of deep oceans, we can get to negative degrees C even without salt because of the pressure effects on this stuff. Not a whole lot, but it's kind of water's weird stuff. And so, one other consequences you might expect from land and water having different heat capacities is how big the seasonality is. So this is just seasons going and coming. So this is 45 C, super hot, and that's minus 25 C. So you can see the seasons in the extratropics on land are pretty big, like 60 degrees C. How about in the ocean? No, it's not moving anymore. The seasons have stopped. All right. In the oceans, that is going, back and forth like here to there. So it's not changing temperature nearly as much. And that's because the heat capacity of water is much higher. And it's also because when you try and cool ocean water, what happens to the cold water? It goes down because it's more dense and it gets replaced with warmer water from below. And then you have to cool that and it gets replaced with, so you're not just contacting the surface, you're contacting an entire column of water. And so there's more heat capacity because it's more mass per unit volume, it's more heat capacity because there's more heat capacity per unit mass, and there's more heat capacity because you're contacting like hundreds of meters of water, whereas the land, it's just like the upper couple centimeters that you're heating. Well, actually, I guess the upper meter or so that you're heating and cooling over the seasons. So you're contacting more of the volume, plus more of the mass, plus more heat capacity all the way through. So the changes are much bigger on land than they are in the water.
Sorry, maybe I misheard this. So when you measure the land temperature, do you measure like the actual land or the air?
So this is land surface temperature, which is measured by the black body radiation coming back from the land. So it is effectively the radiation temperature of the solid, but that solid is in touch with a little bit of air that it's matched to. But you would have a different temperature at 2 meters, say. So this is really the surface, not the air above it. But there's a little bit of air that's kind of down in the soil, in the pockets, that's totally the same as this. And when they're trees and things, it gets really complicated because are you measuring the canopy top or there's a lot of complicated stuff. But anyway, yeah, it's theoretically the solid. Okay. All right. So let's take a look at these equations and then we'll quit. We have talked about the conservation of mass equation. It has the material derivative of density in it. It has the density times the divergence. We talked a little bit about the conservation of salts equation, which talks about the material derivative of salinity, and then extra sources and sinks like chemistry or whenever taking a salt shaker and adding it through the surface or something. Or diffusion actually of salt fits in here. This is the momentum equation, which we're going to talk about a lot more, but we're not going to talk about right now. And then we might say, well, what about the thermodynamic properties? Where's temperature? We don't have temperature up here. Well, we did hear that heat is work and work is heat. So here is heat of that source, the internal energy of the fluid. And here's the term that talked about it doing work. And here is extra energy from radiation or something else. So this is the first law of thermodynamics. Heat is work and work is heat, plus extra energy from other things. And then here is the entropy budget, which, if you forget this one for now, this is the sources of entropy. This basically just says entropy following along on the motion of the fluid stays fixed. So entropy is the stuff that, so what has high entropy and what has low entropy? How many of you have heard about entropy before? Everybody, a little, okay. What has high entropy and what has low entropy? High temperature is more random, it has more states to visit, so it has higher entropy. Absolute zero has low entropy because there's not a lot of states that have absolute zero. And then everywhere in between. Or a jigsaw puzzle at the beginning has high entropy and at the end has low entropy. Because there's only one way to put it together, but there are many ways to have it in the box. So anyway, fluids as they move, aside from heating and cooling and diffusion and that kind of stuff, mixing bits, which would be a source of entropy, the entropy is just conserved as the particle moves around, which isn't quite the same as temperature, because temperature and entropy are related, but they're not the same thing. Okay? So what we would like to do is bring the equation of state, which is the relationship between, in this case, it's density, salinity, and entropy that gives you the internal energy, but I just said it could have also been density expressed as a function of pressure, salinity, and temperature, which is another equation of state, totally equivalent to this one. So there are a lot of these different flavors. We take that equation of state, and then we can interpret certain parts of this as either the temperature or the pressure. So the derivative of this guy with respect to entropy at fixed density and salinity is the temperature. And the derivative of this guy with respect to 1 over the density, alpha, holding the entropy and salinity fixed, is the pressure. So these are kind of mystical, strange things from thermodynamics, which are super complicated. But what we're going to do is we're going to make a version of a temperature that takes both this bit and this compressibility together and makes this equation and this equation collapse and become only one equation that we have to worry about, and it's going to be the conservation of potential temperature. And it's not exact, but it is an approximate rewriting of the equations of motion that's pretty suitable for most of the oceanographic kinds of motion. And it makes us just think, oh, when my particle moves around, it's conserving its entropy. That means it has constant potential temperature. And when it's moving around, it's changing its energy and it's doing work as it's getting compressed and squeezed, which changes the local temperature, but it doesn't change the potential temperature, the temperature it could potentially have if it goes to a particular pressure level. So this is kind of a weird concept. So we're going to come back to it and we're going to talk more about it, but it means that we basically can write a temperature budget that looks just like the salinity budget in our model and forget about all of this complexity and just do that. And we can heat it up or cool it off in units of that ARC flux of radiation. That's all, and then we're off and running. We can forget about all of these budgets. We have everything in nice, simple mass, salinity, temperature, and eventually momentum equations to solve in our model. Okay? And I know that's totally weird and it doesn't make any sense, but it'll start making sense later. Okay. How many of you have heard of potential temperature in the atmosphere or something else before? Some of you. Okay. It's the same idea. It's just a little more abstract in seawater because we can't use the ideal gas law to make it obvious what it is. It's like a weird other thing that we have to write with calculus, and then we can figure out there are equations for it, but you don't want to look at those equations. You don't learn much from that. But in some intuitive sense, it works just like temperature, except it doesn't change when you compress it. Okay. Next time, we will talk about lots of other things. Temperature and stratification in bits and pieces. And also pillows and bricks, which if you guys have heard about this class before, pillows and bricks are key to understanding hydrostatic balance.